Okay, so now in this lecture, we're going to talk about some specific types of gas chromatography detectors that are used to produce the chromatogram upon elution of volatile solutes from a GC column. And there's some different terms that you need to first familiarize yourself with. The first being a universal detector as opposed to a specific detector, right? So a universal detector is going to be one that is able to detect all types of solutes, no matter whether they are organic hydrocarbons or halogenated compounds or inorganic species. While a specific detector is going to be only able to respond and produce a signal for compounds of certain functional group types. So some groups or some molecules are going to go silent or unnoticed with a specific detector. Two more terms are when the detector is destructive versus non-destructive. Okay, so destructive detector is going to, in the process of creating a chromatogram or producing a signal, the compound is somehow going to undergo a reaction or a process that destroys its structure. So we would only use a destructive detector for an analytical purpose where you're simply trying to measure perhaps the concentration or the components in a mixture. You're not actually trying to prepare that mixture or separate that mixture into different compounds for later use. If you were trying to do a preparative type GC experiment where you separate out volatile solutes, then you would use a non-destructive detector, which means it preserves the structures of the compounds that are solutes. And those compounds can then be used for later experiments. So there are three main GC detectors that are commonly used, and you should be able to characterize them. Thermal conductivity is the first. Thermal conductivity detectors are going to be universal in that they respond to all solute types, and that is a huge advantage of why we might use them. And then flame ionization detectors, these are not universal. They only respond to compounds that are reduced hydrocarbons or organic hydrocarbons. In other words, the structure must have a bunch of carbon-carbon and carbon-hydrogen bonds to be detected by a flame ionization process. And finally, electron capture. This also is specific to certain functional group types. Okay, mostly it's going to respond to electronegative atoms in organic molecules, especially halogenated compounds, those containing bromine, chlorine, fluorine, etc. So another advantage of thermal conductivity is that this is not destructive, or it preserves the structure of the solute, and that can be used as a preparative process for later experiments with that same solute. Whereas flame ionization is destructive. It burns the hydrocarbon in hydrogen and oxygen. And electron capture is not destructive. It can also be used in a preparative type technique. The thermal conductivity does have a downfall in that it has very low sensitivity. Flame ionization has higher sensitivity, lower limits of detection, and the electron capture by far is the most sensitive method to detect compounds as they elute from a GC column. So let me talk a bit more about some of the various ways that these detectors work. Okay, so thermal conductivity, generally you'll have a mobile phase of helium, sometimes it could be hydrogen, and these have carrier gases or carrier gas conductivities that are quite high. And as a solute comes out of the column or elutes, it causes the conductivity to drop. Eventually that will lead to a change in the voltage that is being read and producing the chromatogram. So changes in voltage will be detected or will be resemblant of a compound eluting and it not being pure helium or hydrogen gas. And thermal conductivity detectors, as I mentioned, are universal, non-destructive, and those two attributes make them very commonly used. However, they have low sensitivity, or it's difficult to accurately measure low concentrations. Flame ionization, these are now going to be specific for hydrocarbons or organic molecules, where there's N number of carbons, M number of hydrogens, and perhaps other elements in the chain. And if you take some sort of hydrocarbon, such as heptane, and you react it with a mixture of hydrogen and oxygen and air, what you'll get is CH radicals, or lone electrons on carbons, which are then thought to make these CHO cations plus electrons are released. So we're actually burning this hydrocarbon, and that's producing this CHO radical, which then will give a signal. So for this process to work, you must have a highly reduced hydrocarbon with a bunch of CH and CC bonds. As I mentioned, this is more sensitive and better at detecting low concentrations than thermal conductivity. However, because it does combust or burn the compound, is destructive, and that compound cannot be collected at the end of the experiment and used for other purposes. And of course, because it's only specific for organics, we would classify it as non-universal or a specific detector. Then finally, electron capture. Okay, this method is going to be best when you have electronegative atoms that will accept electron density. So it uses what's known as a beta particle. Okay, beta particle has 0 mass and a -1 charge. And the electronegative atoms in compounds such as conjugated carbonyls, nitro compounds, nitriles, and halogenated compounds like alkyl fluorides, these are all going to respond and accept beta particles, which then produces a signal. They are highly sensitive, and of the 3 detectors we've discussed, these are the best at measuring very low concentrations. But, of course, they are specific, non-universal, because you must have the electronegative atom in your compound for it to respond at all. So, if you're asked to determine the best detector in GC to separate each of the following compounds from a mixture, if you're separating these noble gases, which are not organic compounds and do not have electronegative atoms, here we would have to use a universal detector to separate and detect krypton from argon from neon, or you would use thermal conductivity. And you would see that the conductivity would decrease as each of these gases is eluted from the column, since they all have lower conductivities than helium gas. If you're then trying to separate and measure pentane as it elutes compared to butanol, as compared to 1-hexene, these are all organic compounds that are highly reduced hydrocarbons, right? Or we have 5 carbons and 12 hydrogens in pentane, 4 carbons, 10 hydrogens in oxygen and butanol, and then 6 carbons and 12 hydrogens in this alkene. So here you would use flame ionization and combust these in a mixture of hydrogen and oxygen gas to produce those CHO radicals or CHO cations, and that would lead to your signal. Finally, if you're trying to separate and then detect the elution of the following compounds: a ketone, which has an electronegative oxygen, a nitro, which is a very strong electron withdrawing group with electronegative nitrogen and oxygen, and then this conjugated carbonyl, where you have halogens and electronegative oxygen. This is going to be best measured by the electron capture method. These electronegative atoms will accept electron density or essentially react with incoming beta particles. And that will be used to produce a chromatogram, or there will be a response from that. So you don't need to know a whole lot about the mechanics of each of these methods. They are quite complex, but you should know the general overview, and please be comfortable not only describing the types of compounds that they are specific for, or those who are universal, but you should also be able to complete this chart and know the specificity, the destructive nature, and the sensitivity of each method. So for more practice with gas chromatography, you can visit Unit 2 of my analytical course guide at chemguides.com.